Welcome everybody to this new week of big data. Today is going to be a bit special because you should have received an email at 2 p.m. about the course evaluation. So you know that every year we evaluate the courses and every other year we evaluate the exam. So it's a way to get feedback, to keep improving things. It's an opportunity to give comments. So as suggested by the rectorate, we can take 15 minutes now for you to open this email and fill in the form of the course evaluation, right? So I'll give you 15 minutes and we'll start the actual teaching today at 2:30. All right, thank you very much. All right, welcome back. So it's now 2:30. So thank you very much for filling the form. And now we will start with today's topic. So today is special because we are going to see something new. I told you at the very beginning of the course that there are data shapes, there are trees, there are tables, there are graphs, and there are cubes. But in the lecture so far, we've seen tables, the ones that you saw at the bachelor's level with the good old SQL databases, and we've seen trees. So the trees are this way of denormalizing the data for large scales, and so we like to have collections of trees on data lakes. And so we looked into plenty of technologies in order to do that. So we looked at the storage level with HDFS, S3, and so on, how you can store the data on a data lake, as opposed to a proprietary format in a database that manages everything. Then we saw that you can process denormalized data using Spark or MapReduce in batches and in parallel. Then we saw that you can also design proprietary storage front ends, such as not front end database management systems, such as MongoDB, that allows you to update the data at a fine grained level. So as contrasted to a data lake, the opposite of a data lake. And then we saw how to query denormalized data. We saw that SQL actually has limits. SQL was designed to query tables. And if you want to query collections of trees, you need something different that can deal with the nestedness and the heterogeneity. And the language that we used in this course is JSONic. But as I told you, there's probably by now 30 more. And one day it will probably consolidate. But if you learn JSONic, you will be able to very easily learn any other language that does the same thing. So we are right now looking into RumbleDB. The TA team is about to release the quizzes, exercises, so that you can use it. So RumbleDB will work on your laptop. So the exercises will be on your laptop, right? You can actually, all you need to do is download a big jar file in Java, make sure you have Java 11 installed, and then you just run a Java command, and there you go. Everything is in the jar. You have Spark that is in the jar. You don't need to worry about anything. Normally, it should just work. And then as a second step, but this is optional more so that you can play with it, you also will get credits, or already got credit for the Azure cluster, and you can trigger a few machines there. You can put some data, probably the GitHub data set, and you can try again the queries, the same ones that you had in the exercises on your laptop. But now you can try them on the clouds. And of course, if you're on the cloud, you can query more data. And it turns out that the GitHub archive data set has so much data that probably you will not be able to query it all, right? So take it as a game that you're trying to query as much as you can, so you can download every hour of data, hour by hour. So you can try to put as many hours as you can of the data set on your storage, and then you can try to query it. And maybe you can tell us how much you manage to query, send an email to the TA team when you manage, and we'll see who manages to query the biggest part of that data set. All right, but this is optional because the goal is just to play, so that you have experience a bit with a cluster and that you see how it feels to actually use a cluster. Some of you will also learn that you have to remember to shut down your machines. I'm pretty sure a few of you will forget to do it, but this is fine because it's a safe environment, right? It will just trigger a stop to your credits, and then you can just send an email so that we give you a bit more, right? But this is also a way to learn the lesson along the way. All right, but where are we now? We have two shapes that we haven't looked at, graphs and cubes. Graphs is for this week, cubes is for next week. And then you'll have seen the 4 structured or semi-structured shapes. And as for the 5th one, some of you already saw it in information retrieval, and then you'll have the complete picture of data shapes. Okay, so let's then dive into graph databases. So typically, when people talk about the NoSQL paradigm, they will show you these 4 technologies. You know, that this is basically NoSQL, not only SQL. They will mention key value stores. They will mention column stores or white column stores. They will mention document stores, and they will mention triple stores or graph databases. Well, now you probably feel comfortable with that because we've actually looked at that, right? We've looked into DynamoDB, we've looked into HBase, we've looked into MongoDB. So now you're pretty much familiar with all of these, right? And now we'll also look at this last one. But it's very important to keep in mind that this picture with the 4 kinds of data stores or technologies, these 4 are not at the same level in terms of logical, physical level, right? You really need to be aware that a triple store, a document store is at a higher level because this is collection of trees and this is graphs. A key value store is very physical. It's a low level kind of storage that just allows you to store key value pairs. You can get, put, delete, and that's it, right? But otherwise the values are black boxes. So you wouldn't call that a database. You would call that a primitive data store, a low level data store. White column stores, it's a little bit the same, right? It would be tempting to say it's just like PostgreSQL or just like a relational database management system, but actually it wouldn't be completely true. A lot of people use a column store, a white column store, also as a storage. They kind of use it as a better HDFS, right? It's like as if you had HDFS as a storage, except that with HBase, you get on top of that random access and the ability to add and remove according to a single key, right? So it's like an enhanced version of HDFS or cloud storage. But people wouldn't necessarily consider them as top-level databases as the rest. Okay, but what I want to say with this picture is we are going to look at graphs now. In order to motivate why we look at graphs, if we look back at a relational database, you learned in your bachelor's level about normal forms. We also learned in that lecture that we can throw away the normal form. So now you're comfortable with both. But if you do have a database with a high normal form, 3rd normal form, for example, then what you're going to have is multiple tables, right? In that case, 3 tables. And what happens is that these tables can be joined to each other, right? And with this normal form, you can efficiently update and delete and insert data in there because you don't have to deal with anomalies, right? So this is the good old traditional databases of the 70s, relational database management systems. So you have these joins. The problem is that joins are very expensive, right? It's not that, you know, in complexity, you could do it in linear time, a join, right? You can use the hash and so on. So there are known algorithms to do it in linear time, but it doesn't mean that it's actually as fast as a selection or a projection, right? You really have a very high constant, I would say. So joins can be expensive. And in fact, it has to do with the fact that even though you probably heard of entity relationship models and you know how you model data in a relational database, that some tables correspond to entities, some other tables are relationships. Like in that case, you would have an entity on the left, an entity on the right, then a relationship in the middle that connects them, right? So this is in that case N to M, in the sense that any number of tuples on the left can be associated with any numbers of tuples on the right. And then you know you have 1 to n and n to 1, right? But if you have 1 to n and n to 1, you would just use foreign keys in the same table, right? In that case, you wouldn't use a separate relationship table. But anyway, this is the entity relationship way of doing things. And the paradox is that even though we teach entity relationships in the context of relational databases are not that good at relationships. So why is that? They are called relational databases after all, right? But the thing is that even if you try to use techniques that we've seen, because you know the fact that joining is expensive, we know how to solve it. Just drop the normal forms, put it down to the 0th normal form, right? And then you have nestedness and so on, and then you're done, right? But it's not that simple, because when you do that, when you nest things, you have a direction, you have an arrow in the data. You can go down, right? You can associate, you're at some level, then you can go down the levels, but it's one way. So basically you could do this in a nesting fashion, right? You could take this and then nest this table into this one, nest this table into this one, nest this one into this one. The problem is that in reality, you sometimes need to go to in the other direction as well, right? So it's not that you just follow a foreign key to a primary key, but sometimes you need to go in the other direction too, right? And the problem is that in order to support that use case, you need more indices, right? You need to index if you want to very rapidly traverse. Do not imagine a full scan here. Imagine just like you have one tuple and you're trying to follow here from that tuple, follow here, follow there, and then the other direction as well, follow in the other direction. You would need indices for doing that efficiently, right? That every time you look that up here, if you have an index on that column, you can reverse look up that tuple. And again, you take that value. If you have an index on that column, you can very quickly retrieve the value there and so on. But that takes a lot of space to build indices. So this is also not completely satisfactory. And on top of that, in order to build indices, you need to know in advance what indices you want to build, right? You cannot just wait until the user comes and does a query. You need to know in advance the sort of patterns that you have. So you don't have that much flexibility in the system. And so the core question that the graph database people started asking is, what if the links there would be more direct, not going through a full scan of a table, not going through an index like B+3 or hash index in order to retrieve the nodes? What is the most direct way that we have in a computer to follow a relationship? Pointers, exactly. That's the idea. What if we use pointers? That's exactly the idea of graph databases. So the core concept in graph databases is called index-free adjacency. It means that we directly use pointers in memory. We have these structures like that. We follow the pointers. There is no index anymore. No hash index, no B+3 index, at least not for this use case, right? So then if you're here, you just follow pointer, follow pointer, follow pointer. It's just hops in memory, O of one, just like the ones you're used to if you program, especially in C or C++, right? So this is super efficient. So what if we could just fit the data in memory in that way, and when we query the data, we just follow pointers in memory, right? So that's a radical change, and in fact, that's exactly what graph databases are doing. So you see, this is a graph basically. Now you're looking at the tuples as nodes, and you have edges. You can follow the arrows between the edges. So there are plenty of technologies that emerge, but you can basically, at the moment today, it might still evolve, but today there are two, how should I call them? Maybe schools of thought, to be neutral. Two schools of thought for graph databases. There's the school of thought of so-called labeled property graph models in graph databases, and there is the school of thought of the triple store. So the use case for labeled property graph, or the technology that we are going to look at, is Neo4j, but there are also others, but this is probably the one people would think of if you think of the labeled property graph. For triple stores, it would be all, you've already seen W3C earlier, right? They are the standardization body of the web, and they also have a standard for triple stores known as RDF, and we'll also cover this a little bit. Who heard of RDF, triple stores? Some of you, okay. So we'll cover the two of them. And I'll try, of course, it's only 1 week, right? We are not going to spend several weeks, but I just want you to have some sort of intuition, of high-level intuition of what a graph database is and what the landscape is between the two. There are huge debates. It's just like between XML and JSON, or between VI and Emacs, or, you know, so people are a bit fighting over this, like which is the better way. Should we do triple stores? Should we do property graphs? There are even people that say you shouldn't even be using labeled property graphs. You should use a relational database instead, right? So I try to also make you understand why people are arguing in that way, so that, you know, for critical thinking, it's also important, right? Okay. And another aspect that is very important to understand, but this is not just true for graphs, it's actually true for any database technology. Whenever you create a new data model on some specific shape, something totally new, and you develop a query language and a model and a type system and so on, and now you want to implement it. What do? Well, you have two solutions. The first solution is to take an existing database backend, an existing one, and you implement on top of that. So for example, you could take a relational database management system, and you could just implement a triple store on top of that. That's one way of doing that. You can do the same thing, and some people tried it, right, with denormalized data. They try to fit it into a relational database management system. But basically, what's important to understand is that that database backend you're using is actually in the background, that's a physical level, right? You are at the physical level with that relational database management system, the logical level being your new model, in that case, graphs, right? And the second way that you can do things is to not use an existing database backend, just do it from scratch entirely. So it means you build a brand new piece of software that handles the whole thing from storage to the disks, storage on the disk as files, and the entire paradigm re-implemented. Neo4j does that. They re-implemented everything from scratch from the ground up. It didn't start like that. Originally, Neo4j was a Java library, right, that allowed you to create graphs, and then they added a persistency layer and so on. And now they ended up with a fully native graph database. Typically, the order in which things happen when there is a new technology or a new data shape, I don't know if there will be one in 5 or 10 years, maybe one of you will invent one, but typically it's much easier to start with the implementation on top of an existing database backend to try to map things, and then later to come up with a native implementation. Why do we like native implementations? We like them because they can be much faster. Because if you take care of everything, you have more control. But they take more time to build. So this is the reason why it's more pragmatic to start using an existing backend on a physical level. All right? Okay, so the first half of this lecture will be on labeled property graphs and Neo4j, and we'll see there's also a query language for this. And then the second half, maybe today if we manage, or otherwise tomorrow, will be on triple stores. All right, so let's start with the notion of a graph, because this is a graph database. Who is familiar with graph theory? A lot of you. Okay, that's going to be easy then. Who is not? Some of you. Okay, so I'll make sure to bring you up to date, but very quickly. Let's do it like cooking, right? Where, you know, in the cooking, some people like to put their ingredients, you know, in their kitchen, and then they use it in order to bake a cake or whatever. So what we need is a couple of nodes and a couple of edges, and then we can assemble them in a graphs, right? So the nodes are just mathematically, they are an abstraction. They are just things that you call nodes, right? They are mathematical objects that you call nodes. The edges connect one node to another node, right? So they point from some place to some other place, right? Typically, the edges can be directed. Here there is an arrow, so it goes from here to here. And then when you actually take nodes and connect them, then you get this kind of structure. This is called a directed graph. Mathematically, I think mathematicians like to define it as a set of nodes that they call N or V, if they call them vertices, and a set of edges that they call E, and E is a subset of the Cartesian products on nodes times nodes, right? So it's just a subset of all the potential edges that you can have, but of course you don't have all of the possible edges. You have some of the possible edges, right? So this is what you call a graph, right? It's a set of vertices, and it's a set of edges that are a subset of the Cartesian product of vertices times vertices. But you also have graphs that don't have an orientation, right? That don't have any direction. So you just connect two nodes, but there is no specific direction. So this is called undirected graph, as opposed to directed graph, right? So you need to be aware of that. So now, in terms of theory, this is all what mathematicians are interested in, right? You have that, and you can actually do plenty of very interesting things, like trying to find the shortest path, trying to solve for, hope I get it right, the max flow and mean cut. I always tend to invert them. So these are the kind of problems that can be extremely challenging and interesting mathematically. But as computer scientists, what we are also interested in is how to store these things on machines. And so there are a few ways that you can store them, a few naive ways, right, that you can create a program rapidly in Java or C++ or whatever language you like, Python. One way, for example, is to list the nodes. you give them names, right? ABC, ABC. And then in a second column, so these are just structures, right? Like Java objects. Then you have a node's name that is a string, and then you have a list of edges. And more precisely, this is one side of one, the from part of the edge, and then you just put the to parts, right? So here you have from A to nowhere, it's the empty list because A doesn't go anywhere. B goes to A and to C, so you just put a list of A and C as the destination points of the two edges. And then you have from C to A, so from C to A, right? So this is one way to store it. There is another one, like that, when you have some sort of square matrix with all the nodes here and the nodes there, then you put ones or zeros in there, right? So for example, A, all zeros in there in that column, so it goes nowhere. In the column of B, you see there is going to A and going to C. So you see column-wise, you see the edges, and from C to A with a one. So this is an equivalent way of storing the graph. Another one is a matrix that is this time rectangular. I mean, it's just a coincidence that it's a square here, but generally it's rectangular, where you have the nodes on one side and the edges on the other side. And then you just need some encoding that says, you know, -1 is the where it starts and 1 is where it ends, right? So you have the first edge that goes from B to A, -1 to 1, the second one from C to A, and the third one from B to C, right? Of course, as you might imagine, this one is not very efficient because you're going to have zeros everywhere. Plus, you have to enforce consistency constraints because that implies, for example, that you can only have exactly once the number 1 and the number -1 in every column and so on, right? So basically, there are plenty of ways of actually storing these things. But of course, if you want a graph database management system, you probably want to innovate and find new ways. So we'll actually see that there are other ways of actually storing the graphs in a way that we can actually query the data. Okay, but when I talked about the model for Neo4j, I didn't just say it's a graph. I said it's a labeled property graph. So there are other things that come on top of the graph that mathematicians don't typically have, even though, of course, what mathematicians can do with a graph, for example, they can color it, right? This node is red, this node is blue, this node is green. And again, you have plenty of mathematical problems. So you could have colors on the graph. So you can annotate the graph with more things. So this is what we are doing here with properties and labels. So now I'm going to explain to you how the model looks like for properties and labels. This is all the logical level. What you have to map it to, what I'm explaining here, this is the model for graphs. You have to put that in perspective with the model, for example, for relational tables. Relational tables, the model would be that you have rows and you have columns. You can call the rows also tuples or records. Then you can define a relational table as a relation over the domains of the columns, for example, or you can define a relational table as a set of maps that all have the same supports. You know, this is the way. Then you can have tree collections of trees, and then a tree, basically every node has children, you know, and so on and so on. And then you can navigate in JSON seen as a tree. So you can also have a model in that way. So here we are defining also a model for graph databases. So let's start with the notion of a property graph. So that's a graph that has additional properties. So a graph that's with nodes and edges, but now we have these orange bubbles on top of that annotate both the nodes and the edges. You can have them at both places. So what is a property like that, or a set of properties? In that case, we have a node that has 3 properties. A property is a key and a value, right? A key and a value. So we have one property that is named Einstein. We have a second property that is first name Albert, and a third property that says profession physicist. Right? So these are 3 properties. The intuition that I want to give you when you see a node like that is annotated with properties, put it in your mind in the same box as a row in a relational table, because this is kind of the way that it nicely maps if you want to convert between a relational database and a graph database. So what happens is that when you have these properties, these 3 properties here, here, and here, they mostly correspond to one row where you have name Einstein, first name Albert, profession physicist, right? It's a map, basically. So here it's one map. It's a relational table with just one row. But there are two things that you need to consider, two important differences. First, in Neo4j, as far as I know, the keys can repeat. So there is not the constraints that a key must be unique, right? So you can have several keys. That's not the first time we see that. In MapReduce, it's the same, right? In MapReduce, we also have collections of key values, and we allow the keys to repeat if they want to repeat. That's the first thing. The second thing is that in the case of Neo4j, you cannot nest. So you are in the first normal form. You cannot have tables nested in there. So all of these values must be atomic, right? You cannot have a table in a table in a table in there. That's the second thing. This is flat. This is a flat row. So every node can be seen as a record, a one row in a relational table. For who is that clear? Okay. That's very important to make that connection. So the next thing that we add, because of course that will not bring us very far to have one row at a time. The second thing is the labels. Every node in the graph database does not have to, but can have labels. It can have 0, 1, 2, or more labels. So I put them as colors. So mathematicians might think of them as, for example, colors or shape, you know, a square, circle, triangle, and so on, anything you want. So you can label your nodes. So it sounds a bit very abstract, but again, you will understand immediately when I contrast this with relational databases. So now this is my node again. So I had a node with these three properties right there. What did I add? I added two labels here. One label is person, and the other label is in Switzerland, right? You can call them whatever you want, your labels. So these are two labels. What are the labels for? And here, I hope you're going to have an aha moment, because this is really the thing that you must, you know, when you relate graph databases with relational databases, this is how it works. You should think of the label on a node as the name of a relational table, if you want to have a correspondence between the two. For example, if you have in the graph database three nodes, as shown on the left, that are all labeled as scientist, and it turns out that because whoever designed that database was actually doing it with some design in mind and had some structure, right? So you can notice that all of these nodes have the same properties here: name, first name, profession, name, first name, profession, name, first name, profession. And every node would correspond to a database record, right? So the first one is Albert Einstein, then you have Marianne Mirzakhani, then you have Alan Turing, and so on. So these are three people. But the way that this would map, if you would store it instead in a relational database, would be as a table with three rows, three tuples, one for every node. The columns here corresponds to the properties that they share, and the name of the relational table is scientist. This is how it maps, right? So it's very important to understand that if you take a relational database, you should be able to convert it in a natural way to a graph database. We have a question over there. Okay, doing it in two hops then.
Just a quick question. So then could it happen that for this label, in this case, scientist, does it allow to have a node that has the scientist label, but actually has different properties? Does it then map it to the same the imaginary table?
Yes, it is a lot. It is a lot, absolutely. This is why this mapping here is for your intuition. It's basically, let me say it's a one-way mapping. Let me put it that way. If you start on the right and take a relational table, you can convert it to something like is on the left. Who would be able to do that? Right, okay, so you can do that in one direction. But you're absolutely correct that in the other direction, it's only going to work under some assumptions. And indeed, one assumption is that you have the same properties in there and so on, that they have the same types and so on. But if you think of that, it's not very different from the assumptions under which a collection of trees is a table, right? The idea that all the maps within the set of maps must have identical support, the idea that the domains must be the same and so on. So these are all normalization features, right? If you have the data is normalized, or another way to put it is if you have a schema. And in fact, as far as I know, Neo4j and graph databases allow you to define schemas and constraints. So it is possible to say you want, for the nodes that have the label scientist, you want to enforce these properties, and you want to enforce that, for example, the 3 of them are strings, for example. Then you have a schema. But the idea is that just like document stores, schemas are optional. You don't have to have them. So if you want to go the other direction, you need a schema. And if you do have a schema that ensures this kind of constraints, that they all have the same properties and they all have the same types, then you can map things back to the beautiful world of relational databases. Okay. Checking the time. So I think it's time to take a break. I will say a few more words about this mapping because this is actually the reason why some people are critical of graph databases done that way, because many people say that whoever does this in a graph database, whoever is storing data like this, shouldn't be using a graph database in the first place. They should use a relational database, right? So there is some criticism about that this should be done this way, if indeed there is structure like that, right? But again, there is debate, and hopefully you can also maybe contribute to the debate with all the knowledge that you will have acquired. All right, so let's take 15 minutes of break, and I'll see you at 3:15 for the continuation.